Okay guys, I want to give you a bit of a summary of complex numbers, assuming you know the very basics, but we're going to look at converting between standard and polar forms, look at basic operations in standard and polar forms, look at Euler's theorem, de Moivre's theorem, and roots of complex numbers. Actually, we won't look at Euler's theorem. Complex number has the form z equals a plus bi. The a part is the real component, sometimes written as REZ, and BI is the imaginary component. Just in case you've forgotten, I is the square root of -1, which doesn't give a real answer, so that's the imaginary component. Okay, moving on. We can also write the complex number as R times cos theta plus I sine theta. Where that comes from is easy if you look at it graphically. This is not a Cartesian diagram, not an xy plane, but a real imaginary plane, or an argand diagram. And you see the complex number is represented by the red line there. The red line is Z, line segment, sorry, and it's A plus BI. If you think about that, R is the modulus of the complex number, or its length, and the length, and you can see using Pythagoras' rule, it's a squared plus b squared, and if you take the square root of that, that will give you what R is. And the angle is the angle with the positive real axis, which, if you think about that, it's opposite over adjacent is tan, so B over A is tan theta. So there we go, easy to convert. So you can write the same complex number in 4 different forms: A plus BI, or R cos theta plus I sine theta. This cis form is just a shorthand way of writing what's above, and sometimes we like to use the Euler form, which is e to the power I theta. Where that comes from and why that is, we're not really going to discuss. We're just going to consider it as shorthand notation, and you'll see why it's useful in a minute. It's kind of a complex proof, but if you've got 2 complex numbers, Z1 and Z2, if you multiply them together, the resulting complex number will be product of R1 and R2 times cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. How does that work? Well, we can do it by using our distributive law here. And then taking out a common factor of I, grouping the real terms and the imaginary terms, using a compound angle formula, you'll get your proof. Okay, if I hadn't shown you all that, that's quite complicated. An easier way to do it is put everything into the Euler form. When you multiply this together, obviously R1 times R2 is there, and you multiply the e's. Well, when you're multiplying 2 powers together, you've got to add the exponents, and then take out the common factor of I, and then there you go. Very simply, rewrite it in your cis format, and that's your proof done. Okay, you can pause the video and have a longer look at that if you need to. De Moivre's theorem, 3 different notations. It's a powerful theorem that can be really useful. I'm not going to prove it now, and you don't really need to be able to prove it, but you could use the same method as I've just shown you with the previous theorem. Basically, if you, instead of multiplying two complex numbers together, if you raise a complex number to a certain power, then you raise the r to the same power and multiply theta by that power. And as it is in three different formats. It's useful in things like this. We've got a complex number raised to a power. Okay, if I was going to use the distributive law to do that, that would take me a long time. Instead, I'm going to say, okay, root 3 squared plus 1 squared is 4, square root of 4 is 2, that's my r. Negative root 3 over 1, if we take the tan of that, we get negative pi on 3. So that's my complex number in cis form. Okay, using de Moivre's theorem, I'm going to raise the r to the power 3 and multiply theta by 3. 8 cis negative pi. Oh, there it is again. Yeah, and because of negative pi is negative 1, and sine of negative pi is 0, this complex number cubed gives us a nice real number answer. Here's a couple of examples of finding the roots. Find the cubic roots. So if z equals negative 8 plus 8i, what is the cube root of z? Well, if we work that out, and you can do that yourself, work out what r is and what theta is. I put a 2k pi there because you can go around the circle many times as you like, so that's why the 2k pi is there. Because 2 pi is once around the circle, so k is many times around the circle. 2k pi, sorry, is many times around the circle. Okay. W cubed equals z. So the cubic roots of z is w. So I'm raising it to the z to the power of 1/3. Okay, now de Moivre's theorem tells me that I raise the r to the power of 1/3 and I multiply theta by 1/3. Let's see what happens with the theta there. I just wrote, instead of 8 root 2, I wrote 2 to the power of 7 on 2, just make it a bit easier for myself. Okay, so we get 2 to the power of 7 on 6, cis pi on 4 plus 2k pi on 3. And that's my answer. So, cubic roots, there's got to be a few of them. There's got to be 3 of them. And that is the 3 of them. Okay. And we can see it graphically here. They have the same magnitude. That's why I've drawn the circle. That circle there is radius 2 to the power of 7 on 6. And then we've got our 3 different angles. And they're equally spaced around that circle. You have to think about, why is k only 0, 1, and 2? Why isn't it also 3 and 4 and 5? Well, I know there's going to be 3 roots because it's cubic. So that's one answer. But also, if you take a higher number, it's just going to give you the same answer as these, because they're equally spaced around the circle. Here's another example. 6 roots. That equals negative 64. You could draw this on a graph and see what it looks like, but we won't do that. Okay. We know it's a complex number because the square root of the negative number is I. So the 6th root of a negative number is going to be something I as well. Okay, put it in cis form, in polar form, and just just like before, k is going to be 0 to 5 because there's going to be 6 roots. So w, the roots we're looking for, have to be z to the power 1/6. Using de Moivre's theorem, we can simplify it a bit. Simplify it a bit more. Now we'll work out what our 6 roots are. Okay, subbing in the 6 different values for k. And now, just to check, you don't have to do this, but we'll do it quickly because we've done it already. On a Argand diagram, there you go, you can see the 6 equally spaced roots of the same magnitude on a radius of 2 from the origin there. And yeah, that's it. Okay. Some tricky stuff, but once you know the method, you can just follow through. Alright, good luck.